The universe is vast and mysterious. It stretches beyond our imagination, filled with countless stars, galaxies, and cosmic wonders that boggle the mind. The sheer scale and complexity of the universe have fascinated humans for centuries, leading us to ponder the ultimate question: where did it all come from? How did it all begin? This question has intrigued scientists, philosophers, and curious minds throughout history. Various theories have been proposed, but one stands out as the most widely accepted explanation. The prevailing scientific theory is the Big Bang. This groundbreaking idea revolutionized our understanding of the cosmos and provided a coherent framework for explaining the universe's origins. This theory suggests that the universe originated from an extremely hot, dense state. Imagine a singularity, a point of infinite density and temperature, where all the matter and energy of the universe were concentrated.
Imagine a point smaller than an atom containing all the matter and energy that exists today. This tiny point, often referred to as a singularity, held the potential for everything we see around us. About 13.8 billion years ago, this point expanded rapidly. This event, known as the Big Bang, marked the beginning of the universe as we know it. This expansion wasn't an explosion into existing space. Instead, it was the expansion of space itself, a concept that can be challenging to grasp. Instead, it was the expansion of space itself. Space and time were created in this monumental event, giving rise to the dimensions we experience today. The Big Bang created space and time as we know them. It set the stage for the formation of galaxies, stars, planets, and ultimately life. It also set the stage for the formation of everything we observe in the cosmos. From the smallest particles to the largest structures, the Big Bang laid the foundation for the universe's intricate tapestry.
The Big Bang theory is supported by numerous observations. Over the years, scientists have gathered compelling evidence that reinforces this model. Scientists have detected the faint afterglow of the Big Bang. This afterglow, known as the cosmic microwave background radiation, serves as a crucial piece of evidence. This afterglow, called the cosmic microwave background radiation, provides a snapshot of the early universe. It offers a glimpse into the conditions that prevailed shortly after the Big Bang. The distribution of elements in the universe also aligns with Big Bang predictions. The abundance of light elements like hydrogen and helium matches the theoretical calculations.
The Big Bang theory isn't a complete explanation. It raises many questions. For instance, what caused the Big Bang? What existed before it? These are profound mysteries that continue to challenge our understanding. What caused the Big Bang? What existed before it? These questions delve into the very nature of existence and the limits of our knowledge. These are questions that scientists are still trying to answer. The quest for knowledge drives researchers to explore the farthest reaches of space and the deepest realms of theoretical physics. However, the Big Bang theory remains our best model for understanding the origin and evolution of the universe. It provides a framework that explains many of the observations we make and continues to be refined as new discoveries are made. The Big Bang theory starts with a concept that is difficult to grasp: the singularity. Imagine all the matter and energy in the universe compressed into an infinitely small point. This point, called the singularity, had infinite density and temperature. It's a concept that pushes the limits of our current understanding of physics. The singularity represents the very beginning of time and space. Before the singularity, there was no space, no time, and no laws of physics as we know them. The singularity is the ultimate mystery, a point where our current theories break down. Scientists believe that the laws of physics as we understand them cannot describe the singularity itself. The conditions were so extreme that they require a new theory of quantum gravity. This theory would combine Einstein's theory of general relativity with quantum mechanics. It would help us understand the behavior of gravity at the quantum level. Despite the challenges, scientists are actively researching the nature of the singularity. They are developing new theories and conducting experiments to probe the fundamental nature of gravity. Understanding the singularity is crucial to unlocking the secrets of the universe's birth.
In the first fraction of a second after the Big Bang, the universe underwent an extraordinary period of expansion known as the inflationary epoch. This epoch is one of the most fascinating and mysterious periods in the history of the cosmos, where the universe expanded at an unimaginable rate. During this incredibly short period, the universe expanded at an exponential rate. Imagine the universe growing faster than the speed of light, stretching space itself in a way that defies our everyday understanding of physics. It grew from a size smaller than an atom to a size larger than our solar system in a tiny fraction of a second. This rapid expansion is almost incomprehensible, but it set the stage for everything that would follow in the universe's evolution. This rapid expansion was driven by a hypothetical field called the inflaton field. The inflaton field is a concept in theoretical physics that helps explain how such a dramatic expansion could occur. As the inflaton field decayed, it released a tremendous amount of energy. This energy was not just any energy. It was the driving force behind the universe's rapid growth, providing the necessary push to expand space at such an incredible rate. This energy fueled the universe's exponential growth. Without this energy, the universe might not have expanded in the way it did, and the cosmos as we know it could have been vastly different. The inflationary epoch is crucial for explaining several observed features of the universe. It provides a framework for understanding why the universe looks the way it does today. One such feature is the universe's remarkable uniformity. Despite the vastness of the cosmos, matter and energy are distributed in a surprisingly even manner. The inflationary epoch smoothed out any initial irregularities in the distribution of matter and energy. The smoothing effect is essential for the uniformity we observe in the cosmic microwave background radiation. This resulted in the remarkably uniform cosmic microwave background radiation we observe today. The cosmic microwave background is a snapshot of the universe when it was just 380,000 years old, and its uniformity is a direct consequence of the inflationary epoch. The inflationary epoch also explains the origin of the large-scale structures in the universe. These structures include galaxies, galaxy clusters, and the vast cosmic web that connects them. Tiny quantum fluctuations during inflation were stretched to enormous sizes. These fluctuations, though minuscule in the beginning, were amplified by the rapid expansion of the universe. These fluctuations became the seeds for the formation of galaxies and galaxy clusters. Over billions of years, these seeds grew into the complex structures we see in the universe today. The inflationary epoch, though brief, played a pivotal role in shaping the universe we see today. It set the initial conditions for the cosmos, influencing everything from the distribution of galaxies to the uniformity of the cosmic microwave background. Without this brief but crucial period, the universe might be a very different place. The Section 4, a universe of particles, from quarks to atoms. As the universe expanded and cooled after the inflationary epoch, energy began to convert into matter. This marked the beginning of a particle era, where the universe was a hot, dense soup of fundamental particles. Initially, the universe was too hot for even atoms to exist. Instead, it was filled with quarks, leptons, and their antiparticles. As the universe continued to cool, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. This process, called nucleosynthesis, occurred within the first few minutes after the Big Bang. During this time, the universe was hot enough for nuclear fusion to occur. Protons and neutrons fused to form the nuclei of light elements, primarily hydrogen and helium. These elements, forged in the early universe, would later become the raw materials for stars and galaxies. However, the early universe was still too hot for electrons to bind to nuclei and form stable atoms. The universe remained a plasma, a sea of charged particles, for hundreds of thousands of years. The formation of atoms would mark a crucial turning point in the universe's evolution.
Section 5. The Cosmic Dawn, a first glimpse of the early universe. This chapter takes us on a journey back in time to the very beginnings of everything we know. After about 380,000 years, the universe had cooled enough for electrons to combine with atomic nuclei. This cooling process was a significant milestone in the universe's history. This event, known as recombination, marked a profound change in the universe's properties. It was a turning point that set the stage for the universe as we see it today. Before recombination, the universe was opaque. It was a hot, dense plasma where light couldn't travel freely. Photons, the particles of light, were constantly scattered by free electrons. This scattering kept the universe in a state of opacity, preventing light from traveling far. After recombination, the universe became transparent. This transparency allowed photons to travel vast distances without being scattered. Photons were free to travel through space without being scattered. This newfound freedom of photons marked the beginning of a new era in the universe's history. This marked the moment when the first atoms formed and the universe transitioned from a plasma to a neutral gas. The formation of these atoms was crucial for the development of the universe's structure. The photons released during recombination have been traveling through the universe ever since. Their journey has been long and uninterrupted, carrying with them the story of the early universe. Today, we detect them as the cosmic microwave background radiation, or CMB. The CMB is a faint glow that fills the universe, providing a window into the past. The CMB provides us with a snapshot of the universe as it was just 380,000 years after the Big Bang. This snapshot is a treasure trove of information for scientists. The CMB is remarkably uniform, with only tiny temperature fluctuations. These fluctuations are incredibly important for understanding the early universe. These fluctuations, representing slight variations in the density of the early universe, provide crucial information about the early universe's composition and evolution. They help us understand how the universe evolved from a hot, dense state to the vast cosmos we see today. They are the seeds from which all the large-scale structures in the universe, such as galaxies and galaxy clusters, would eventually form. These tiny variations grew over time, leading to the formation of the complex structures we observe in the universe today. The study of these fluctuations continues to be a key area of research in cosmology, helping us unravel the mysteries of the universe's origins and its ultimate fate.